The fractional knapsack problem. There are n items. The weight of the ith item is Wi, which is greater than 0, and given the profit or price of ith item Pi, which is greater than 0, the capacity of knapsack is M. Okay, in the fractional knapsack problem, you are permitted to break the item and take a fraction. So the quantity xi you are putting in the knapsack, it can be greater than or equal to 0 and less than or equal to 1, and this will contribute a weight of xi into wi to the knapsack capacity and pi into xi to the total profit. The task is maximize sigma I equal to 1 to n xi into pi subjected to sigma I equal to 1 to n xi wi less than or equal to m. The weight should not exceed the knapsack capacity. The solution for this problem is the x is the resultant array. We are expecting the result, how much quantity, how much block or units of the ith item is taken. It is shown through the array x. Initially we make everything 0, that is nothing put in the knapsack. Then C is equal to M. M is the capacity of the knapsack. Then we are trying to pick the items I equal to 1 to n. If the remaining capacity of the knapsack is less than the item to be picked, we have to drop the attempt. Okay. If the capacity is greater or equal to Wi, that is the capacity, the remaining capacity of the knapsack is greater than or equal to the item we are planning to pick is higher, then we can take one complete unit of or complete block of that item. So we are making xi equal to 1. Then we will update the remaining capacity. We will decrement the weight of that item from the remaining capacity. We will go for the next item. When the weight of the item is greater than the remaining capacity, we will exit. Then we will check whether we have tried all the items or not. If we have not tried all the items, we will pick a fraction of the item we have tried to put in knapsack. After filling this knapsack, we will calculate the profit by multiplying the xi value with the profit of the item xi. Our task is prove that if the items are sorted in descending order of Pi by Wi, that is P1 by W1 is greater than P2 by W2, greater than P3 by W3, that last item Pn by Wn, then the algorithm generates an optimal solution for the given instance of the knapsack problem. That is our task. If the solution provided by our algorithm is some x equal to there are n items, 1, 2, 3, 4, n. It is like this: 1, 1, 1, and 3 by 4. Sorry. 1. All the cells are 1. Okay, that means we were able to pick one complete blocks of all the items. Remember, if you are unable to pick, you are not permitted to pick more than one block, and if you can't pick, or the remaining capacity of the knapsack won't permit you to take one complete block, you can break the item and take a fraction. Okay. If your algorithm gave a situation an x like this, we can say this is optimal. This is optimal. Powering on. Suppose the solution given by this algorithm is something like this. You have picked item 1, a complete block, 2, a complete block, third item, a complete block, and 3 by 4th of the fourth item. 1, 2, 3, 4. At this point, the knapsack capacity is S hosted, and the remaining cells will be 0. You are unable to pick fifth item. You are unable to pick sixth item. Okay, this will be a possible solution. So at this time, a person came with the argument that the solution was not optimal. He is able to give another solution. That means remember our task is within that capacity we have to maximize the profit. So he is saying his solution, let us call his solution y. Okay, let's call this person y, and the solution by him is y, and he is saying the solution by him is the optimal one. Okay, see our solution, we were able to pick the first three items, the whole block, and we were able to pick the fourth item, 3 by 4 of that block. That is, after putting these three items in the knapsack, we were unable to pick one complete block of fourth item. So we have broken it and taken 3 by 4 of that block. Okay. So let us check what are the possibilities of his solution, his argument. Okay. First, let us check. Will it be something like this? That is 1, 2, 3, 4, 5 up to in 1, 2, 3, 4, 5. We were able to pick first three items completely, 1, 2, 3, first three items, and 3 by 4 to the fourth item. Okay, this was our solution. Can this solution be something like this? 1 by 2, half of a block of fifth item, and some 1 by fourth of the sixth item, like this. Is this possible? So what we are saying is a solution proposed by person Y, can it be something like this? So up to this, the for cell, it is similar to or same as our solution. That is, we have picked the first three items, then 3 by 4 of the block of the fourth item. Okay. After that, he is saying he was able to pick the half the block of fifth item and 1 by fourth of the sixth item. And this has more profit than our solution. He is claiming that. Is this possible? We know in our solution, we picked 3 by 4 of the block because we can't take one complete block of fourth item. Yes, and remember that. Then after placing 3 by 4 of the block of the fourth item, our knapsack capacity is over. That is why we could not pick the item 5. Okay. So at this point, the knapsack capacity is exhausted. So, why the person Y can't take a single piece of fifth item and sixth item, because at this point his knapsack capacity also over exhausted. Okay, so this is not possible. So the solution proposed by the person Y cannot be something like this. Okay, so after exhausting the knapsack capacity, he can't pick a single piece of the next items. Okay. Then let us check another possibility. Can it be something like this? 1, 2, 3. He picked x1 one block, x2 one block, x3 one block. In our solution, we picked x4 3 by 4 of the block. Okay. In his solution, he is saying he picked 1 by 4th of the fourth item. We know he can pick 3 by 4th of the fourth item, but he didn't do that. He picked 1 by 4th of the fourth item, and there is space in his knapsack, isn't it? He can pick 3 by 4, but he picked only 1 by 4. So there is remaining capacity. He picked some, let us say, some 0.23 of the block of fifth item and 0.33 block of sixth item, and small pieces of the remaining items. Okay, like this he continued. Is this possible? And I didn't pick the last items. Okay, so it will be something like this. Is this possible? We can agree with this claim because this is possible. That is, at the fourth cell, or trying to pick the fourth item, it is possible to pick 3 by 4th of the block of the x4 item 4, but he has taken 1 by 4th of that block. So there is capacity, so he can pick the remaining items, some small quantities of remaining items. This is possible. So this is possible. Okay. Then let us check another possibility. First item he pick one complete block. Second item he didn't pick a complete block, he picked half. Third item he picked 1 by 4. And fourth item he picked uh, point some 3 portion. So definitely we know capacity is there in the knapsack. You can pick more items. Fifth item he picked 0.37 part, and sixth item he picked some 0.16 part. Okay, he can continue like this. Okay, at some point his back capacity will be exhausted, and hereafter he can't pick items. Okay, he can't pick items. 0.6 or something like this. Okay, so this is also possible. Then let us check what is the difference between our solution X and the solutions proposed by person Y. See, at some point you remember X was 1 1 1. Let us verify that 1 1 1, and the fourth item is 3 by. After that everything 0. Okay, this was X. Then what is the difference between this our solution, the solution given by the algorithm, and the solution proposed by the person Y? You can see the difference happens at a point before this 4 cell. Okay, let us call this J. Let us call this J. The difference occurred at a cell before J, isn't it? Let us call them K. Okay, let us call that cell. Here the first difference happened. In this solution proposed by person Y, here the first difference happened. Okay, so the cell where the value of our solution, that is X, it differ in a cell K, so the least cell is always less than J. Okay, the difference happen at a cell with index less than J, isn't it? So this is not possible. These are the cells with indices higher than J. So this is not possible. These two possibilities we can agree. So in this proposed solutions, the difference happens at K, and K is always less than or equal to J. The difference start at kth in Y's solution, and this value of K is always less than or equal to J. It's equal to J in this case, and it is less than J in this case. Okay, let us take the second solution proposed by the third one. Okay, the first one, this is not possible. This is the let this be the second one, and this be the third one. Okay, let us pick the third solution proposed by Y. Okay, that is 1, then 1 by 2, 1 by 4, the second item 1 by 2, the third item 1 by 4, then the fourth item some 0.33 portion, next item 0.23, that it goes. Okay. This is thus a solution proposed by Y. Okay. What was our solution? It is equal to 1, 1, 1, and in the fourth cell it is 3 by 4th of the fourth item. Okay, this was our solution. Okay. Next, we are asking Y to increase the value at the cell K. Okay, here the difference starts. Okay, we are asking Y to increase this item, the quantity of this item, or add some more of item 2 to make it this cell value, that is Y of K is equal to X of K. We are asking him to make by adding some Q quantity of Q blocks of some Q block. Okay, let's write it. Q blocks of item 2. Okay, so he says at this point his knapsack capacity is exhausted, so he can't pick remaining items. Okay, so everything 0. If we ask to add some more quantity to this item 2, he has to decrease the quantity of item 3, item 4, item 5, like that, isn't it? Because to adjust the weight or capacity of the knapsack. So he has to take some Q1 quantity from K plus 1, K plus 1 item, this item, K plus 1 cell, and here to decrease some Q2 block from K plus 2, then Q3 amount from K plus 3. Okay, then only you can adjust the capacity of the knapsack. That is the quantity added to the kth cell, that is the item 2. He has added Q block of item 2 to make this Yk equal to Xk. So that is equal to Q1 plus Q2 plus Q3, isn't it? So this much added, that should be equal to quantities are removed. Okay, so after doing this, we will be getting another solution. Let us call it set. That is, he has added some quantity Q to make these two values are equal, and he has added Q1 quantity here. He has added 0.33 plus q2 quantity here. Okay, so we will be getting another solution called set. Okay, now uh, comparing set with our solution, that is the solution provided by our algorithm, it is in the first cell they are equal and the second cell they are equal. Okay, the remaining cells he has removed certain quantity. Okay, sorry, this is minus. He has to subtract, not add, he has to subtract. He adds something here, he has to take the other items. After that knapsack, then only the weight will be adjusted. So then thinking about the profit, which one will have higher profit, Z or Y? Next, let us think about the profit of Y and profit of Z. Which is higher? You have obtained profit set, obtained the solution set by adding something whose Pi by Wi value is higher than the Pi by Wi value of the items removed. Okay, then which is having higher profit? You have added some quantity of the second item that is having higher Pi by Wi value, that is added, and you have removed the equivalent weight. Then you are getting set. So set will be having more profit, isn't it? You have added something to Y and you removed less profit items. Okay, so profit of the solution set will be higher. Okay, that means there is a solution, that means there is a solution same as that of Y, but with greater profit. Then we can say Y is not optimal. Then we can say the claim of the person Y is not correct, because by adjusting the weight we can get another solution whose profit is more. So Y is not optimal. Okay, and if we repeat this, that is this time we made this yk equal to xk. Okay, so these two cells are same now in our solution and in Y solution. So next time we repeat the same thing by making these two cells equal. Okay, we will be getting another solution, some set dash, which will be having higher profit than Z. Okay, and we continue this. So we will be reaching, finally we will be reaching this solution. Okay, so we can prove that we have proved that our solution X, it is the optimal one. There is no other solutions which will give higher profit than X. So, and this is proved.